Okay, today we covered two topics that set up the analysis that we're going to need next week for the Bernoulli equation. The first was the discussion of streamlines, streak lines, and path lines. And each of these are simply tools by which we can try to describe the velocity field or the flow field in a moving fluid. Streamlines are lines that are everywhere tangent to the local velocity vectors. And so in blue I'm showing what might be the local velocity vectors. The black lines would be the streamlines. Next I'll talk about path lines. Path lines are the lines followed by a particle that's released into the flow and then tracked over time. In a steady flow, the particles will follow the streamlines, and those two are comparable. Finally, streak lines are lines formed when you continuously release particles at a particular location. And so think of like a smokestack that at some later time you take a snapshot. So this is a line made up of a whole bunch of individual particles that have been released continuously from one point. Again, in steady flow, all three lines are exactly the same, but in unsteady flow, they will diverge. And the example that I did in lecture illustrated that. Okay, the other topic that we covered in lecture today was accelerations. And in the accelerations, what we really need to focus on is the fact that the velocity field, the flow field of the fluid, is u, v, w are the three components of the velocity, and each of them is a function of space, so three spatial dimensions potentially. That's supposed to be a z, and time. So x, y, z, and t. So same is true for v, function of x, y, z, and time, and w, function of x, y, z, and time. So the acceleration vector, which is the total time derivative of the velocity vector, needs to account for both the time variability and the implicit time variability that's created by spatial variations. Nice example of this that I talked about in lecture is flow through a constriction, where we go from velocity 1 into velocity 2, where velocity 2 is greater than velocity 1. That means that a particle in the fluid that starts out at velocity 1, as it moves along, it accelerates into this constriction. And so there's an acceleration it experiences due to the spatial variation. How do we capture that mathematically? Well, we just use the chain rule as applied. Sorry, I'm having a problem with the color. Okay, so applying the chain rule to the total velocity, we can say that let's just consider the x component of velocity, or of accelerations, which would be the total time derivative of the x component of velocity, which means we take the direct partial derivative of u with respect to time, so we need direct spatial dependence, plus, now using the chain rule, du dx, dx dt, du dy, dy dt, and du dz, dz dt. Finally, to finish this, we note that dx dt is just u, dy dt is v, and dz dt is w. So the resulting expression for the x component of the acceleration, du dt, plus u du dx, plus v du dy, plus w du dz. And I'll conclude this summary by noting that this first term, the time derivative with respect to time, the partial derivative with respect to time, is called the local acceleration. The other three are called the convective accelerations.